So we've seen how to use induction to prove things. Today I want to talk about how we can also use induction to define things. So in this video I'll talk about using induction to define functions, and in another video I'll talk about how we can actually define sets using induction as well. So today let's talk about defining functions. So to define a function, you could say inductively. We can also use the word recursively. How do we do this? The first thing is that we specify a base case. In the base case, we define a function on some kind of initial values. It could be a single value, it could be multiple values, just like sometimes we use a single base case or multiple base cases. And then in the inductive step, we define the output, or I'll say define the function on other values by, we're going to specify its output in terms of its output on previous values. Okay, so let's do a quick example. So let's let f be a function from natural numbers to the natural numbers, defined by, I'm going to say f of 0 is equal to 3, and f of n plus 1 is equal to 2 times f of n plus 3. Okay, so this is an inductive definition of f, or we could say a recursive definition. This is the base case, so we've defined the value of the function on some particular initial value, in this case 0. And then for any other value that's not 0, we're going to define the output of f on some n plus 1 in terms of its output on a previous value. So notice how here we're defining f on n plus 1, n is smaller than n plus 1, and so that would count as a previous value. And I claim that this is a valid definition of this function. This uniquely defines the function on all natural numbers. Why is that, or how would we argue that? Using induction, of course. So in the base case, obviously the function is defined for 0. And in the inductive step, we would say, well, suppose that the function is defined for n, then it's defined for n plus 1, because here it is, assuming it's defined for n, this formula says how to define it for n plus 1. Therefore, by induction, this function is defined on all natural numbers. So, for example, right, we have f of 0 is 3, f of 1 is going to be 2 times f of 0 plus 3, which is 2 times 3 plus 3 is 9, and then f of 2 is 2 times f of 1 plus 3, which is 2 times 9, 18 plus 3 is 21, and so on. And you can see that, right, at each step we already know the value of the function on the previous number, and then we can use that to figure out what it is on the next number. Just as an aside, I will mention, right, I keep using the words induction and recursion kind of interchangeably, saying, oh, we're defining this inductively, or we could say we're defining it recursively. Typically, people use the word recursion when they're talking about computation or they're talking about functions. And people use the word induction when they're talking about a proof. But in a very deep sense, these are the same thing. So for example, you can think, one way to think of an inductive proof is that it is a function that outputs a proof. It's a recursive function that outputs a proof. So let's do another example. Another example I'm going to do is the Fibonacci numbers, and we've seen these many times before, but let's think about how they fit into this same pattern. So we're going to let, I'll call it capital F, is again a function from the natural numbers to natural numbers, right? Be the function that gives the nth Fibonacci number. Right, then we would define it like this. We say f of 0 is 0, f of 1 is 1, and f of, we'll say f of n plus 2 is equal to f of n plus 1 plus f of n. Right, so again, this is a valid definition of this function for all natural numbers. And again, we would, if we wanted to formally prove that, I mean, it's because of strong induction, right? We gave two base cases, and then assuming these are defined, it's going to define the function on the next number. So a couple things to point out. One is, this shows that we can also use this to define sequences. A sequence really is just a function where the input is a natural number. You say, oh, I want the fifth thing in the sequence. You put 5 into the function and you get out the term which is the fifth thing in the sequence. It shows that these Fibonacci numbers that we've been thinking about, and all these sequences we've been thinking about, they also fit into this this framework of defining things inductively. So if we have a function that is defined inductively and we want to prove things about it, typically we of course would use a proof by induction. Proving things about recursively or inductively defined things most naturally is going to be expressed using a proof by induction. And we've seen examples of that for the Fibonacci numbers, right? We've proved several things about Fibonacci numbers, and we do them by induction, and the reason is that the Fibonacci numbers are defined inductively. I'll leave you with one to try yourself, so something you might try proving about this. So as an exercise, prove that for all natural numbers, f of n is equal to 3 times 2 to the n plus 1 minus 1. So this is an, if we think of this, we can think of this as a sequence, right? This is a recursive definition of the sequence. This is a closed form definition. So see if you can prove, using induction of course, that this is always going to be true, that these values are going to be defined by this formula.